Hello and welcome back to Mrs. O'Graham's Maths. We are going through the Practice External Assessment number 2 from the D&D Resources for the complex numbers external. And thank you to D&D for allowing me to use these resources and create these worked solutions for you. For question 1a, this little section of the video looks a bit different. I've needed to do an update for a change in the question from the original. So we've got complex numbers u and v that are given to us just here. U has a p in it, whereas v is just a regular complex number, and we're told that u divided by v makes 4 plus 9i. And from there we've got enough information to work out the value of p. So u divided by v is 2p plus i over 1 minus 2i, and that's got to be equal to 4 plus 9i. So we can bring up the 1 minus 2i and multiply it like this. Now that's easy to do on the calculator. So 4 plus 9i times by 1 minus 2i, like so, is 22 plus I. Now if we compare the real part, on the left we have 2p must be equal to 22, so therefore p is 11. Okay, part B, if we are doing a division and it's already in polar form, this actually becomes very straightforward. So we can do v over u. First of all, if we're dividing in polar form, we are going to divide the modulus and subtract the argument. Just make sure you get these two the right way round and know which one you are doing first. Okay, so 8 over 2 is 4, and 2 over k minus 1 over k would be 1 over k, so that is pi by k. Next we have the a locus question, and we have two modulus set equal to each other. We'll start by making z equal to x plus iy. That's frequently the best starting point for locus questions if you are not super confident on the geometry of them. Sometimes the geometry of them is very easy to do, and that's my preferred method, but most of the time you're going to need to do a lengthy bit of algebra where we turn z into x plus iy first. So then the modulus of z minus I equal to z minus 2 modulus. We're now going to pop in the x plus iy, so it would be x plus iy minus I, x plus iy minus 2, and remember that modulus of z will be the square root of the real part squared plus the imaginary coefficient squared, not the I, just the coefficient. That's the definition of modulus, and you need to memorize that. Okay, so the real part on the left hand side we have is x squared. On the imaginary stuff we have y minus 1, and that gets squared. Then we would do the square root. On the right we have x minus 2 are the real parts, and y for the imaginary part, and that gets squared. So now you can see if I've got a square on both sides, square rooted on both sides, I can square both sides and just remove the square root symbol. Now we need to work through this so that what we're aiming for is to get the equation of a straight line. That's what it means when we are describing this locus, and also we're given this information here that we need to find the y-intercept of that line, so that gives us a clue also that we're going for a straight line. So what I'm going to aim for is try and put this algebra that we currently have down here into an equation that is y equals something. Okay, so this is the sort of next steps of working now. We're into the next pieces. we've got y squared minus 2y plus 1. And then expanding this bracket, we've got x squared minus 4x plus 4. So that x squared cancels with that one. The y squareds cancel. And we have minus 2y is equal to minus 4x plus 4, and subtract the 1 from the left-hand side. So we'll have a plus 3. So y will be equal to, I'm going to divide everything through by negative 2, so we have 2x minus 3 over 2. And the question asked us for the y-intercept, so we just need to make sure we finish that. And that's negative 3 over 2. Okay, part D. The most common problems that I see coming up with these sorts of questions is we know we need to square both sides at some point, but when we've got a plus or a minus in between, then it's easy to forget that you have what's essentially a bracket that's being multiplied by itself, and forgetting the middle terms that come out of that. So I'll just show you what I mean with this. If we square both sides to try and remove the square root, we have 2 root x minus root k squared. Now it's best if you actually write that out as 2 brackets like this, because then you'll see that it's like when you multiply out the brackets of a quadratic, where it's easy to forget this one times this one if you're just squaring both sides. So if we square the left, we get 4 x minus k. Now that is actually another place where it's easy to make a mistake and only square the square root part, but the 2 is also being squared. So that one gives us a 4 there. On to expanding the bracket on the right. First we have this one, 2 times the root x, and we will get 4 times x, because root x times x will cancel out to x. Then we have 2 times the negative k here, so that'll be negative 2 root k x root k. Then we have this one where we have the same, negative 2 root x root k. And then we have the final term there. So that will be plus root k times root k, which is k. So this becomes 4x minus 4 root xk plus k. And this one is 4x minus 4k. Now we have that 4x cancels with the 4x there. And we are trying to solve x in terms of k, so we want the x terms over to the left and the k terms over to the right. So let's bring the 4 root, I'm actually going to leave it as root x root k because I need to separate the x in a second. We'll bring that to the left, and then on the right we have 4k plus k, so that's 5k. So then root x equals 5k over 4 root k. So x is equal to that squared. So we have 25k squared over 16k, which simplifies to 25k over 16. All right, for this excellence question, we need to solve this squared equation. So we want to find the square root of this. Now that is most easily done in polar form using de Moivre's theorem. So the first thing we need to do is try and translate that into polar form. before we can figure out where it sits on the Argand diagram to do that, we do need to rationalize out the denominator. So root 3 plus I over AI times it by minus AI over minus AI, because when we rationalize the denominator, we multiply out by the negative of the imaginary part. So that will equal minus a root 3I and then minus AI squared all over negative a squared I squared. So this becomes, let's see, minus a root 3I. I squared is minus 1, so this is a plus a. And similarly on the bottom, with I squared being minus 1, this is a squared. Now we can divide through by a singular a to simplify. So this is minus root 3I plus 1. And in fact, I'm going to write it the other way around just to make it easier. 1 minus root 3I, because we're used to seeing things in that order, all over a. Okay, now thinking about it on an Argand diagram, we have in its real and imaginary pieces, it would look like this. So we're in the positive x direction and the negative y direction. So in the x direction, we go over by 1 over a, and in the y direction, it will be root 3 over a. So we are somewhere like this. So then our triangle to get there looks like this, and we have theta just there. So z squared in polar form will be the modulus and then the angle. So this triangle that we've got going on there, that's based on the triangle that's got a length of 1 and a length of root 3, and then the hypotenuse would be 2. That triangle is on your formula sheet for the special identity triangles, and it gives us this angle here of pi by 3. Now the triangle that we have exactly is actually 1 over a, root 3 over a, which makes the hypotenuse 2 over a. So our modulus is 2 over a, and the angle is pi by 3, but it's in the negative direction around here, so it's a negative pi by 3. Okay, now we can do the solutions to z. So the first one is to do the square root of 2 over a, and then we half the modulus. And that's using de Moivre's theorem to find roots. If you're not sure of that, then you can go look up the video, but we take the root of the modulus and we divide the argument by how big our power is. Then for the second solution, think about your Argand diagram again. We have our first solution is just here at minus pi by 6. Solutions of roots are always, like square roots and things like we're doing here, they're always symmetrically rotated around the origin. So our next one will be out here, and because there's 2 of them, then we've got a gap there where we divide the circle by 2, and what we're doing is adding on half of the circle to there. Well, that half of a circle is a pi. So the second solution here, the modulus hasn't changed, the length away from the origin, but our angle will be to take negative pi by 6 and add on a pi. So that gives us cis of 5 pi by 6. Okay, question 2. I want to simplify as far as possible this expression. And because it's an achieved question, I'm just going to go... Oh, actually, no, I can't. So if you have a updated calculator, the newer model than this one I have on my screen, then you could do this on the calculator and it will leave you in third form. I can't, so I'm going to have to do this by hand. My computer calculator doesn't do that. It's an old version. Okay, so let's take you through... Actually, we'll just do it down here. The root 96, we're looking for a square number that goes into 96. Well, you can divide 96 by 16. Now, if you don't get that straight away, you can do a smaller number, and you just keep going until you find something that will work for you. So root 96 is 16 times 6. Root 50, the square number that comes out of that is 25. So that can be 25 times 2. And then root 18, we can take a 9 out of that, like this. Okay, so root 16 is 4, root 25 is 5, and root 9 is 3. I just made a mistake. 9 to make 18, it's 9 times 2, not 3. So let's just fix that up. On the top we have 4 root 6. On the bottom we have 5 root 2 minus 3 root 2. So 5 minus 3 is 2, so that's 2 root 2. The 4 over 2 cancels to 2, and we can put the square root over the 6 and the 2 like so. So then it becomes the 2 root 3. Okay, part B, we are solving this quadratic. Now I'm going to do this one on the calculator because it is only an achieved mark. So we can go to equation solver. We've got a polynomial with degree 2. We have a is 1, b is minus 10, c is 31. Now before I hit solve, I'm going to check my setup and go down to complex and change that to be in a plus b form. And now I will solve it. So I get that x is 5 plus 2.45i, or x is 5 minus 2.45i. Now, if you're not confident using your calculator, first of all, I suggest you learn how to do complex roots. That was just by changing my setup here, by going Shift and then Setup, and you can put it into complex mode. For an achieved question, you can do it all on the calculator, and it will be accepted in this decimalized form if the question does not say give your answer in exact form or give an exact answer. If the question says gives an exact answer, you do need to give the square root answer that's given in the solutions in the D&D book. This one would be 5 plus or minus root 6i. That would be required if you're doing anything more than merit. You'd have to show the more than achieved, like a merit question. You'd have to show the algebra way that you got there. So I'll just do that very quickly for you. I would do this by completing the square. If we're looking for complex roots, that's the easier way to do it. So half the 10 and we get 5. That would give us a 25 out of there, so we need to subtract the 25 and a plus 31. So minus 25 plus 31 becomes plus 6. So z minus 5 is equal to plus or minus the square root of negative 6. So z equals 5 plus or minus 6i. Part C, we have u and v. We want to find the argument of u times v. Let's start by working out what u times v is. So this will give us minus a squared I minus a squared I squared. Well, I squared becomes minus 1, so it turns that into a plus. And I'm going to write it with the real part first and the imaginary part second. Now if we pop that onto an Argand diagram, like so, we would be going in the positive direction by a squared on the x-axis, negative direction by a squared on the y-axis. And so our value is that over here, that's where UV is. That gives us an isosceles triangle, which makes that angle there 45 degrees, or pi by 4. Actually, I'm not even going to write the 45 degrees because everything is always preferred in radians, so minus pi by 4. And it's minus because we are going under the x-axis in a clockwise direction. If we go clockwise, it's a negative. All right, now on part D, if you are told one root and it's a complex number, then so our first root is root 3i. Let's just separate that I a little bit. Our second root will always be the conjugate of that complex number. So that means take the imaginary part and make it negative. So that will be negative root 3i. Now we need to work out the a and the b portion in here. So if we substitute in one of those roots, so I'm going to use root 3i as the one that was given to us, then that will give us an answer that satisfies this equation. So it will be equal to 0. So root 2 times root 3 cubed, or root 3 cubed, that would become 3 times root 3. So then timesing it by 2 is 6 root 3. Now I cubed, well, I squared makes minus 1, so let's factorize out one of those. If we take out an I squared, it's minus 1 and times it, so that becomes a minus like this. Next one, we have a minus. Now root 3 squared becomes 3. Times it by the 3, we get 9. I squared becomes minus 1. So times that by minus 1, we get a plus. Then we get a root 3, I, and b equals 0. Now looking at the real and imaginary parts, if we compare the real parts, let's just do this in another color. So the real parts, on the left hand side we have 9 and we have b. On the right hand side we just have 0, so b is equal to minus 9. If we compare the imaginary parts, on the left we have minus 6 root 3 plus a root 3, which equals to 0. We divide everything through by root 3, then we will have that a is equal to 6. Okay, now the final solution, if we pop this into our expression, so 2z cubed minus 2z squared, a was 6, b is minus 9, and then head on over to our equation solver. Just back to here, so we're in equation solver, we're doing a polynomial with degree 3. We've got a 2 minus 2, a 6 minus 9, and solve that, and we have our 3 solutions listed here, which has just given me pause because that's not right. I can tell by this these 2 complex ones not being right. One of them should match the one we've been given. And now this is a good demonstration to show you to check those things and go back and see where I've made the mistake. So let's go back to the expression here. Now that expression doesn't match up here because I accidentally wrote this bit down wrong. So that was not a -2, that's a -3. Now let's fix that into here. And now we'll press solve. And now you can see that the two complex roots that I already knew match with what we've got up here. And the third solution that I didn't know yet is 1.5. So Z3 equals 1.5. That's actually a really good demonstration to check the answers that you're getting out of this. It can help you to find any mistakes that you've made along the way. Okay, part E, we have another locus question. Find the locus of the point representing Z if this thing is purely imaginary. Let's start by figuring out exactly what that thing is doing. So start with Z equals X plus IY. That's your usual starting point, especially if you can't really see what to do with a question. Just pop that in and see what falls out. So then 2 times Z will be 2x plus IY plus I all over x plus IY minus 2. And that is equal to, well, now we need to rationalize out the denominator. So we will have this multiplied by x minus 2 is the real part minus the imaginary part. I'm going to put that in a bracket actually. I think I'd rather do it like this so I can see what's going on. Okay, so next line here. This is going to turn into some fairly tricky algebra. So first I'm going to just collect up this left-hand piece so that it's in real and imaginary parts separately. That 2IY becomes 2YI, and then I'll add on the 1 for where the I is just here. So I've just sort of factorized that into two different pieces of imaginary and real. And then we have x minus 2 plus IY. We're going to again times it by the x minus 2 minus IY, x minus 2 minus IY. Okay, if we multiply that out, we will have 2x, x minus 2, 2y plus 1, x minus 2i, plus 2x times minus iy, so that'll be a minus 2x iy, and then 2y plus 1 I times minus IY. So we have I times I, giving us an I squared, that's a minus 1, times by the minus just here, that will give us a plus 1. Okay, so this one actually turns into this. All over x minus 2 squared minus I squared y squared. The middle term I haven't written out in full here because it would be plus IY times x minus 2 minus IY times x minus 2, so they would cancel. The I squared down here, that turns into a minus 1 and times it by the minus, so it turns that minus into a plus. Now the next bit that I'm going to use to our advantage to save us some effort here is that this is purely imaginary, which means that the real portion of that number will be equal to 0, or rather the real portion of this expression that we just worked out will be 0. So let's take that out. We have 2x over x minus 2, so this is taking all of the real pieces, and we have y 2y plus 1, that's over x minus 2 squared plus y squared. that is equal to 0. Just tidy that. There we go. Now, sorting out this expression, if we bring that up and times it by 0, it will cancel away. So we're only interested in the numerator being equal to 0. So we have 2x squared minus 4x plus 2y squared plus y equals 0. Now we're getting a little bit closer. We can see that this can be put into the format that would give a circle. I'm going to go that extra step to show you what I mean there. That this can be put into the form of, let me write it over here. So remember, circles are x plus a squared and y plus b squared is equal to some number. We could have also constants in front of that bracket there. And if I did completing the square on what we've got here, that's what would happen. So I could take out the 2. That would become x squared minus 2. So then if I half that and square it, that would give me an extra 1 would come out of the squared, and then it would get times by 2, so then we would take off the 2 to make it equivalent. If I do a similar thing over here, we have 2. If I take 2 out of the y, it would be a half y. I then need to half that again for completing the square, so it would look like this. The quarter squared would give me a half. That would be times by 2 to give me the 1, so would subtract 1 and it equal to 0. Now we don't need to go as far as that for this question, because it didn't ask us to put it into that particular form. Often they do, and you would need to step through the last pieces here, but we just need to find the locus. So we can actually stop here because this equation does give us that locus. So at this point here, you can say the locus is a circle, because we have found an expression for a circle which is satisfied by the x and iy that we set z to be in the beginning. Okay, question 3. We are told that we have a remainder of 2 when this is divided by x plus 2. This means we're doing the factor and remainder theorem, which is to say that we put in from this one here that if x plus 2 is being divided, then we try the root of minus 2. So I'm putting in minus 2 for every x. And we're told that that has a remainder of 2, so this will be equal to 2. So I'm just going to pop minus 2 in first. So 2 times that cubed plus 3 times it squared plus 2 times our answer. We get minus 8 plus k equals 2, so k must be 10. B, we have u and v on the Argand diagram. U is 2 minus I, v is minus 1 plus 2i, and we want to work out uv. Well, let's not hurt ourselves with doing any extra work than we need to, so let's pop that into the calculator. So 2 minus I times minus 1 plus 2i. Ooh, I've put something in wrong. There we go, I did the wrong kind of minus in there. That's going to be equal to 5i, and the last bit that often gets forgotten is to plot it onto the diagram. Do not miss that piece there. So we need to put 5i on here, and it's right here. So that there is uv. And on to part C. Start by saying that z is equal to x plus iy, so we end up with x plus iy minus I times x minus I for the conjugate minus I, and that's going to be set equal to 99 minus 12i. Alright, so let's start on this beast of an expansion. So we have x squared minus ixy minus ix, then plus ixy minus I squared y squared minus I squared y, then minus ix plus I squared y plus I squared. Ooh. Okay, let's try tidy that up. First we can do minus ix and ixy there cancels. The minus I squared y and the plus I squared y there. And then I think that's as much as I can do at the moment. So we have x squared, and then I'm going to pull out this piece here, the minus I squared y squared. So I squared is minus 1, times it by a minus, that'll be a plus y squared. Then we have two lots of ix, and then we have a plus I squared, so that's a minus 1 is equal to 99 minus 12i. Now comparing the real and imaginary parts, so the real part of this will be x squared plus y squared minus 1 equals 99, or take the 1 over to the other side, that equals to 100. The imaginary parts on the left, we have only got one, and that is minus 2x, and it's equal to minus 12, so therefore x is equal to 6. Pop that back into the real part. We have 6 squared plus y squared equals 100. So 6 squared is 36. So y squared is equal to 64. Y is equal to plus or minus 8. So therefore z is equal to 6 plus or minus 8i by substituting those values back into the x plus iy here. Okay, we want to find the modulus of w. Let's pop z into it. So we have 2i plus 1 over 2 plus 2i. On the calculator, let's do 1 divided by 2 plus 2i. Since it's got no algebra in there, we'll take the easy option with the calculator. So that is going to be 2i plus a quarter minus a quarter I. The real part is a quarter. The imaginary part is 2 minus a quarter, so 2 minus 1 quarter is 7 over 4. So then the modulus of that is to do the square root of the real part squared plus the imaginary part squared. So a quarter squared is 1/16. This will be 49 over 16. And I'm doing this by hand because we need exact values for this answer. You can't give your answer as a decimal here. And then we would have to square root it. Okay, so pop them together and we've got 50 over 16, which is the square root of 50 over 4. We could probably leave it there, but just for completeness, I'll simplify the 50 as well. We can take 25 out of 50 is 25 times 2. If we bring the 25 out of the square root bracket, we square root it, so it'll be a 5 root 2 over 4. Okay, the last one. We want to show that this will have no real solutions for all values of k. So if we're looking for types of solutions, we need b squared minus 4ac. First, I'm going to need to put that into a quadratic form. So we have everything on the left equal to 0. So we have 3x squared for the x squared, sorry, not 3, just an x squared, I was thinking ahead, for the x squared terms. And then for the x terms, we have 2k. We'll bring this 3 over, so that'll be a minus 3 times x. And for the c term, we have 2k squared plus k plus 7. Now b squared minus 4ac becomes 2k minus 3 squared minus 4 times 1 times 2k squared plus k plus 7. So 4 times 2k squared gives me 8k squared minus 4k minus 28. If we expand this first bracket, we get 4k squared minus 12k plus 9. Which we end up with minus 4k squared minus 16k minus 28, add on 9 is going to be minus 19. Now, if we're thinking about types of solutions, we need to show that this will either always be positive or always be negative or always be equal to 0. And the best way to approach that is by trying to complete the square on it. So take out minus 4 and we get k squared plus 4k here, minus 19, and I'll do completing the square on that portion there. So that'll be k plus 2 squared. That will give us the k squared plus the 4 squared. It also gives us plus 4, so we need to subtract 4 from it. That'll be minus 19. So then multiplying that out, we have minus 4k plus 2 squared plus 16 minus 19. So that ends up being a minus 3. And then we explain it. So k plus 2 squared is always positive because it got squared. Therefore, minus 4k plus 2 squared minus 3 will always be negative because it got times by, so the positive was times by a negative, that turns it into a negative, and then the subtraction is only going to make it more negative. So therefore, b squared minus 4ac will always be negative. Therefore, there are no real roots. All done. All right, join me next time. Maybe look up the other D&D resources that I have if you're studying for level 3 calc. I've got the other videos for the other standards too.